This video is brought to you by mywayteaching.com.
So in this figure, you can see the first one, the rectangular bar. So as I told you, if we increase the depth, unless the load is exactly at the right place, the D bar may be bent, as you can see in this second figure, a thin bar and how it can buckle, isn't it? And this is called as buckling. Okay. So, to avoid this, a common compromise in the cross sectional shape is made, and that is shown in this figure C. Commonly used selection for a load bearing bar. This section it provides a large load bearing surface and enough depth to prevent bending. So this shape it reduces the weight of the beam without sacrificing the strength, and hence even it reduces the cost. Okay. See, use of pillars or columns is also very common in buildings and bridges. A pillar with rounded edges, as you can see in this figure, pillar with rounded edges or rounded ends, we can say, and it supports a less load than the pillar with the distributed shape at the ends, isn't it? By seeing only, you can you can recognize it supports a very less weight compared to this. So the precise design of a bridge or a building has to take into account the conditions under which it will function, the cost and long period reliability of usable materials, etc. Okay. Whenever we are designing a building, we should take care about all these we can say parameters like conditions under which it will function. And even the cost, long period, all these are very important whenever you are designing a building, and even reliability of usable materials. Okay, all these are very important. Why the maximum height of a mountain on earth is approximately equal to 10 kilometer is can also be provided by considering the elastic properties of rocks, see, a mountain base is not under uniform compression, and this provides some sharing stress to the rocks under which they can flow. The stress due to all the material on the top should be less than the critical shearing stress at which rocks flow. And at the bottom of a mountain of height h, the force per unit area due to the weight of the mountain is given by, HPG, where this rho is the density of the material of the mountain, and G is the acceleration. This one is density of the material of the mountain. And G is acceleration due to gravity. So the material at the bottom experiences this force in the vertical direction, and sides of the mountain are free. So this is not the case of pressure, or you can say this is not bulk compression either. This is a shear component, approximately H rho G, we can say. So now the elastic limit for a typical rock is given by 30 into 10 raised to 7 Newton per meter square. So equating this to the HPG, we with the density, that is 3 into 10 raised to 3 kg per meter cube. So it gives H is equal to 30 into 10 raised to 7 Newton per meter square, and density so the height is given by 10 kilometer, which is the more than the height of Mount Everest. Okay.